Good evening, everybody. Welcome to Herding Cats 104. In this session, I'm pleased to have Rodney Black, the author of Cats Back, to do a session on how to wire a layout for signaling. This clinic isn't specific to cats, but rather it gets into block detection, gap placement, turnout control, turnout feedback, and the concepts of lots of other low-level stuff. In a future session, we're going to get more into signaling, and then we're going to start building things in cats. And parallel to this, I am starting to record a series of tutorial videos that will be posted on the YouTube channel, which will be linked from the group page. And I probably won't get those posted until around Thanksgiving, but they are in the works, so they're coming. So at this point, Rodney, if you want to share your screen, I'll turn it over to you and take it away.
Okay, looks like you're going to have to enable screen sharing.
Yeah, I forget to do that, don't I?
No problem.
It's been 3 weeks.
Yeah. Okay, here we go. I thought this slide was a good one to start with, given that we've got COVID-19 restrictions and everything. But anyway, let me welcome you all here. Good evening, good afternoon, good morning, depending upon where you're listening from. But tonight we'll start talking about wiring, and I want to apologize. For the last time I did this, I listened to the recording and my volume was faded. It was a whole lot. It was loud and soft and loud and soft. So I've gone over to a headphone type mic, and hopefully we won't have that problem with the variable of the volume. Okay, let's see. Okay, so cover plate. I'm going to talk about wiring for signals tonight. Outline, I've gone through the introduction. I'm next going to go to planning, some questions as you're wiring up your layout that you'll ask and you'll have to answer yourself. I can't answer them for you, but you'll find that these questions will probably pop up. Then we'll dig down deeper into occupancy detection, gaps, detectors, things like that. I want to spend most of the time probably on turnouts, control, feedback, that kind of thing, because that seems like an area where a lot of people have questions on. In fact, just today I got 2 emails asking about how can I do some things. And I'll lightly then go over signals, lights and semaphores, how you might hook those up, and we'll look at a reference design. Now, Jerry, what I've done tonight is I put this outline, after we did the last one, we had a lot of comments on, well, can we do stuff shorter? Like 10, 15 minutes rather than an hour video and things like that. And then somebody suggests, how about if we put the table, divided into chapters? So what I've done is periodically throughout this talk, you'll see this updated outline. And that's basically where the one chapter ends and the next one begins. So in your editing, maybe this will help you out a little bit. Okay, planning. First question, of course, is what do I want? And that's a very open-ended question. So let's see if I can refine it a little bit and ask some sub-questions about it. First one is, how much interaction do I want on my layout? Am I interested in doing a railfan layout in which you just kind of sit and watch the trains go around, museum type of thing, or even in your home layout? Or am I more interested in operations? But no matter how you answer this question, I think that signals can be applicable and spice up the layout in either case. Of course, they don't make sense if you're doing something like narrow gauge in the mountains or something like that where there weren't any signals. But if you're doing something where signals be appropriate, then this talk is for you. I'm going to go down the operations branch of that question because that tends to be, for me, the more interesting. So you need to think about, well, what's my operating scheme? The simplest and easiest one, of course, is what's called shout and go. And it requires no dispatcher, it requires nothing on your railroad. The way it works is one of your engineers, say he's at Alpha and he wants to go to Baker, he looks down the tracks and he says, doesn't see anybody, so he says, I'm going from Alpha to Baker, and you just take off. Now, we often say that there's a prototype for almost everything we do in this hobby, and I actually did find a prototype for Shout and Go. Near me, there's a railroad, I think it's called the Great Western Beat Company in Loveland, Colorado, and that's basically what they do. I think they use railroad or radios. I don't think they use cell phones, but basically that's the how they operate. If you want to go a little more sophisticated, then we've got something that there's a scheme typically called Mother May I, and in which that you have a dispatcher, and but still you don't need anything on the railroad, and the crew then would call the dispatcher and say, okay, dispatcher, I'm at Alpha and I want to go to Baker, will you clear me? And the dispatcher will say yes or no. Then if you want to go more formal, uh, you can get into timetable and train orders with all the various paperwork. Or if you want to go a little more modern and a little less structured, then you go with something like track warrant control, or sometimes called direct train control. And if you want to go whole hog, you go with CTC. Now you can use signals on all of these. The only one, and they'll spice things up. The only one that really requires signals, of course, is CTC. Okay, so see, let's focus in a little more, then drill down into what's CTC. You need a dispatcher panel. You got a dispatcher, you're going to need a panel of some form. Some people say you can't dispatch unless you can twist the knobs and push the buttons. So then you start looking for a machine. You can build your own. It used to be you could find discarded machines from the prototypes, but those beasts are very rare and getting to be very expensive because they are rare. Or you can simulate a machine. And here we use the photo that's classic one from JMRI, and you simulate the buttons and knobs on your computer screen, or you can go with something more modern. What do you want to do for local control? And things you might think about is how can the dispatcher lock or unlock your turnouts? How do you throw them? Here I illustrated using a Digitrax uh, cab for throwing switches. Can you do field override? In other words, what's on the flasher panel to help you with throwing turnouts? What kind of signals? Semaphores, lights. What are your aspects and indications? I'm not going to go into much in this talk tonight. One of the next ones that we do, we'll go into this in more depth and detail than you want to know. What kind of switch machines are you going to use? You've got a lot of choices here. You got twin coils. You can use tortoises, slow motion type switch machines. You can use servos. And we'll look at what these bring to the table here shortly. How much computer dependence do you want? I have a friend who a well-known in-scale layout close by, and it's been published in a lot of magazines, and he would like to put CTC on it, but he doesn't want to use a computer, and that's going to be a particular challenge for him. But for what we're doing tonight, we're going to focus on a computer-assisted layout wiring. Now we get down to where the rubber meets the road. What can you afford, and how much money do you have to dump into it? Or what can you build? Sometimes you can trade a little bit of money for what you can build, or what can you buy? And so that leads me to what I'm going to call the layout construction ledger. If we look at it kind of like an accountant, what's layout going to cost you? And I'm not talking just money, but the things that go into the cost of layout. The bigger the size is, the more it's going to cost you. Functionality. For example, if you go with a shout and go type of operating scheme, you have less functionality and it'll cost you less. How much prototype fidelity do you want to put into it? In other words, do these signals operate exactly the way the prototype does? It's you're going to pay for it in time or money or something like that, or do you want color position light signals, something like that? Again, very small market, it'll probably cost you more. The higher the track plan complexity, the more it's going to cost you. And I'm sure there are other things as well that enter into the layout cost. On the other side of the ledger, of course, is where your available resources. How much money do you have to drop into it? How much time can you spend if you're young, a young parent or something? You got kids. You typically don't have as much time to spend on the layout as if you're somebody retired like I am. How much skill do you have? Often you can trade time for money if you've got the skills. And of course, how many friends do you have? Don't overlook friends. They're one of the best things that can help you build a layout. And the bottom line, of course, is this. If the layout cost must be less than or equal to your available resources, if it's not, you're going to go bankrupt and the layout probably won't come around. Okay, let's generalize a little bit. From the perspective of things I'm talking about here, we've got a computer. The outputs of the computer, things that JMRI calls turnouts, are used to drive things like set the aspects on a signal, the colors, the Semaphore blade position, used to throw the points on the switch machines. You get inputs to the computer. These are things like your block detectors, your turnout feedback, electrical switches, and we'll look at some more of these in detail. And typically JMRI calls those things sensors. Here's an example of what you might be modeling on the prototype for CTC. This is a control point OS section at East Leiden on the UP's old Moffett route. The things you'll see, let's see if I can bring up the, whoops, yeah, let me go back. I want to bring up my pointer, and for that I gotta find Zoom again. Okay, maybe I'm not going to get it. I'm not going to find it. Oh,
we can see your cursor.
What's that?
We can see the cursor.
You can't see the cursor? Okay, let's use the cursor then. Okay, so on the control point, what do you see? Well, here you've got an exit signal coming out of the siding. Here, and this is on the main line. Here we've got an exit signal coming out of the siding side. You got a bungalow here with your field equipment in it. Good things to model, little details to put on. You got an approach signal for somebody coming into the siding. You got a switch machine. In this case, I believe it's a dual control switch machine. I'll explain what that means in a few minutes. If I was to translate that into a schematic diagram, which we'll be looking at, here's what you'd have on your layout. You got position feedback on the points. These are inputs to the computer program. You've got your exit signals. These are outputs from the computer program. You got the approach signal over here, again, an output. You got block detection, input to the computer. And then you've got this bunch of stuff, which we'll call the switch control, turnout control. You got a switch machine, you got a bunch of push buttons. And I'll try to go over what these are in more detail in a few minutes. So, into chapter 1, let's get into occupancy detection. We're going to look at where you put gaps and what kind of detectors you might have. I split the detectors into basically two broad categories. One we might call an area detector. In other words, it just says that a train is somewhere on this track. And this is fairly typical block detectors, where we use resistor wheel sets and we look for the locomotives and the wheels to change the electrical characteristics of the railroad. There's also, you could call it a point detector. These would be like Hall effect magnets or LEDs, optical detectors, or even perhaps RFID readers in which the train is at a particular point. And these are used more for things like triggering a signal, crossing gates, or saying that I'm under a coal tipple or something like that. Let's talk first about point detectors. And whatever kind of detector you have, the most important thing is that be reliable. Here what I've tried to show, by reliable, I mean that if there's nothing between the optics, the detector should say it's clear. If there is, the optics should say if there is something, they should say it's not clear. It's unreliable if you miss something between the optics. It's unreliable if you have something that's not, if it says there's something there and it's not. And this is about the only place you're going to see cats in this presentation. Now, one characteristic of when using point detectors, the trains must be longer than the longest distance between detectors. But now let me tell you another little story about this. I went down to San Antonio some years ago for Christmas, and my family and I were walking around. We went into one of the attractions, and the module group had set up a layout. It was a good sized HO scale layout, and they had signals on it. And the signals, of course, caught my eye, and I walked up, and my first question was, well, do they work or not? And I watched, the signal was green on a bridge, and I watched the train come through, and the signal dropped to red. Train kept going. Pretty soon the signal went to yellow, and then pretty soon went back to green. I said, well, that's pretty cool. I wonder how they did it. So I watched the train come around again. I watched fairly a couple of cycles. I couldn't really tell. And then the engineer stopped to take a lunch break, and he had stopped the train just after the signal. And I watched it go to yellow after about 30 seconds and go red after 30 seconds. So, okay, I know how he did it. He used a timer on the signal. He used probably an optical detector to trip the timer, and then the timer timed out. But the point of this story is simply this. He used something that was very simple, was very inexpensive, and it achieved the desired effect of what he wanted, what the module group wanted was working signals. And yeah, they weren't prototypical, but I think from what their goal was, that they hit that one out of the park. It worked very well. But if experience is that if you try to use point detectors for block detection, you can do it in a more elaborate type scheme, but you're going to find that you're going to get some complexities in terms of timing, or you have to put in some timers, or you have to start determining direction of travel or things like that. And that's the or you just make sure all your trains are longer than the longest distance between your detectors. Let's talk about block detectors. Again, these tend to be electrical detectors. Again, you want reliability. Up in the corner here, if there's nothing in the block, you want the detector to say there's nothing there, and if there is, you want the detector to find it. It's unreliable if you don't detect cars where they're there. It's unreliable if you get false detections. Now, unlike the point detector, your blocks must be longer than your longest car, or actually, to be more specific, it has to be longer than the longest distance between two detecting wheel sets. If it's not, then basically you get a dropout in the detection. Okay, let's dig down. I'm going to look at block occupancy detectors primarily. So we're going to look at where do you put your block gaps, how do you wire them up, and how do you do power districts. Okay, why do you want to cut gaps? First thing is, I think most of you guys know this kind of stuff, but if you have power routing, uninsulated frogs and power routing points, you have to cut them just so you don't get shorts. That's all I'm saying here. Now, one thing you can do is, I've seen a lot of people do this, you just put a slide switch in here as your mechanism for throwing the points. And with that slide switch, very easily, you use the slide switch to power the points to be the right polarity, depending upon how you set the switch. Okay, other reasons you might want to cut gaps? Well, you may want to isolate the shorts. So in other words, if I had a short over here, I don't want this section of track to short out as well. And if you don't have the gaps in here, then they're all electrically the same, and a short in one place shorts it out in the other. You may want to do power distribution. So you could use a couple of power supplies. For example, I've got, if you have a lot of sound locomotives, you may find that if you put too many of them on one power supply, it's going to they're going to ask for more current than the power supply can handle so you can split your layout up into power districts. And of course, for the one we're most interested in for tonight's talk is you want them for doing train location so that you can identify that the train is in this block as opposed to that block. Where would I do gaps? The general first rule is put signals where you want your train should stop. In this case, you want them to stop before they hit the points. You may want to do intermediate type signals, in which case then you put your gaps where your signals are. The general rule is put the gaps at the signals. The reason being is what you expect to see is as soon as the train passes a signal, it's going to drop the signal to red. Do not put signals behind the gaps. And the reason being is then it'll go red before the train hits the signal. Here's another example. We'll get a little more complex here. Here we've got a little bit of a ladder. I wouldn't put, here's where we violate, we say you don't, every gap doesn't have to have a signal. For example, we have to have gaps here because of the, because of the frog issue. So you might move your signals back here. If you've got facing points, you wouldn't put a signal, here, and you probably wouldn't gap it either. A little more complicated. You got a crossover. You probably gap both ends of the crossover, and you put a gap on the crossover itself. Double crossover, same type of thing. And we get a little more complicated with sidings, and we get perhaps we've got an industry in the middle of out in the middle of nowhere, and you don't want to protect it completely with signals, and we got a yard. In my next talk, in which I talk about signals, I'll give you some rules and give you something more solid by which you can, to show you where you should place gaps in signals. But anyway, those are the general ideas. So let's look at block detection. Here I got some track. I cut my gaps in it. I'm going to wire it up with detectors. So I got block detectors. Track power goes into the block detectors. The block detectors then go into the individual blocks. But since I'm using block detectors, then of course I'm going to want feedback. I want the, when are the detectors detecting, when aren't they? You look at this and you immediately see where the promise of DCC in terms of eliminating wiring goes out the window. Suddenly we're getting a lot of wires underneath our layout. So what some people do is rather than use individual block detectors, you can get a board that has multiple block detectors on a single board. What that does for you eliminates the wiring a lot, because typically then you have just one pair of wires coming out for feedback that go into your return bus or something. You also have then, you've reduced the amount of wires you need for power and so forth. In addition, it tends to be that a board that supports multiple detectors is cheaper than individual block detectors, simply because you get the advantage of sharing the power and the circuit boards and stuff like that. So, but let's look at what happens with shorts, typically with detectors. And these are things to watch out for. So I've got some track, I've got all these, I've got several detectors, I've got power supply powering them all. And I get short, let's say right there. What happens? Well, the detector sees the short, and it says, it basically, it's often very difficult to distinguish between a short and something, a train being in the block. But typically, a short will take the detector down. Sometimes you may get an indication that it's a short versus a detection. And since the detector is shorted, that often shorts out the power supply. Power supply goes down, and all the detectors then fire because they all see the short. In other words, the short propagated from the track through the detector to the power supply, and all your detectors go down. This is often called the Christmas tree effect on a dispatcher panel because what happens is everything lights up at once. How can you avoid that? First of all, you can use a power manager. So in addition to breaking up your layout to power districts, when you get a short, such as here, those detectors go down, but the others don't. So in other words, look at including power managers. Ideally, what you'd like are detectors that basically have circuit breakers in them, so that when one goes down, then it doesn't bring the others down. I think there are now some new products out on the market that do that. I think Digitrax has put some out. So here's what to take away on occupancy detection. Put signals at block gaps, but not all block gaps have signals. A gap, so yeah, a gap need not have a signal because you may use the gap for short isolation, power distribution, effects, things like that. Isolate your security elements, your OS section, your plants. Know that detection eats wires badly, so get lots of wire. Power to districts provide short circuit protection, and plan ahead. Experience tends to indicate the gaps are easy to cut in your track. If you have to come back and put in another block, you can use snips of some type, Dremel tool. Feeders are easy to drop. It tends to be the hard part is hooking up the feeders because you're under the layout and you're dropping wire and you're working on your back and you have hot solder falling on you, stuff like that. So that's all I'm going to say about occupancy detection. Let's look at turnouts, and we're going to look at control and feedback. There are three aspects to turnouts that I want to talk about. One is how do I bend the iron? In other words, how do I actually move the points? Second is how do I get position feedback? And the third is how do I share remote and local control? And I think this is probably one of the least understood and appreciated areas of model railroading until you actually hit it, run into is the remote local control issues. I'm going to start with what I've learned from Dr. Bruce Chubb's stuff he's published, some really good stuff. And if I can distill out what I've got out of it, I'm going to call it the taxonomy of turnouts. He has identified basically 5 kinds of turnouts, and they're distinguished by these characteristics. The simplest is a manual turnout. Think of a switch stand, for example, in a yard or an industry or something like that. How does it work? Well, the crew goes out, he has a key, he unlocks the padlock, removes the padlock, flips the lever, and now he's got the bar that he can move the points with. So the field can control it. There is no dispatcher control. The field unlocks it. The dispatcher can't unlock it. There is no switch machine. Very simple and very inexpensive for you to try to simulate on your layout. The next level up is called an automatic electric lock, and it works very similar. The crew would go out, they would unlock a padlock, they would remove it, they'd open a door, throw a lever, something like that. And what would happen then is that the act of unlocking it would then inform the signaling system that the turnout is unlocked and it's unsafe for trains. They can't go through at track speed. They need to slow down to restrict it, and be careful, look for points or turnouts thrown against them. So again, the field controls it, yes. The field unlocks it, no dispatcher control. You may or you may not have a switch machine or an electric machine of some sort. The next is a controlled electric lock. And the difference between the automatic electric and the controlled is this right here. The dispatcher is involved in the unlocking process. So typically the way it has to work is that the crew would call the dispatcher and say, can I have permission to use, lock 4A or something like that. The dispatcher would do something on the panel to unlock it. And at the same time, then the field crew would go through their padlock routine and unlock it and so forth. The next highest level then is dual control, in which the difference between dual control and controlled electric is this row right here. With dual control, the dispatcher can align the points and as well as unlock them. Then finally, there's power operated, and with power operated, the field has no control at all over the turnout. So consequently, you don't need a dispatcher unlock. Typically, on the real railroad, these going from left to right, you get more expensive, except power operated. So the prototype tends to shy away from the controlled electric and dual control if they can get away with it. But if you're off the CTC, then you just about have to have some type of dispatcher intervention. Okay. Again, let's talk about a very, very simple way to put signals on your layout. And I see a lot of modules groups do this, and you know, again, that's good. Okay, and the circuit diagram is simply something like this. Here we've got our slide switch that we use to throw the turnout. And when the slide switch is in one position, we light up the green LED. When the slide switch is in the other position, we light up the red LED. So consequently, all the signals do is show which way the turnout is lined. And you could put some out here on the frog ends to give you a red when you're not going, when the turnout is lined against you. Now, if we extend that a little bit, you put a voltage across, and you got a couple of places that you can tap off voltage. With this, now you can run this into like a decoder or something. So this then gives you detection on how your feedback is working. This gives you, a point alignment feedback for going into the computer program that controls your signals. When I was young, there was a genre of jokes, which often I guess you could call good bad stories, you know, and it goes something like this: there's a guy in an airplane, and he fell out of the airplane. You say, well, that's bad. Well, he had a parachute. Well, that's good, but the parachute didn't open. Well, that's bad. But there was a hay mound. He was heading for a pile of hay. Well, that's good, and it goes on like this: good, bad, good, bad. Frankly, I don't remember what the punchline was. But when I started looking at, in particular, what Dr. Chubb had done in terms of explaining how turnout control, it was a good bad story about things. They tried things, they didn't work, so they patched it and tried something else, and it goes like this. If you have a manual turnout, the simple switch stand, they're bad out on the main line because a foul turnout does not affect the protecting signal. In other words, the train approaching it doesn't know that it's foul. So somehow you want the switch control to interlock into the signaling system. So that's why they went from manuals to the automatic electric lock, where the act of opening the padlock then told the signaling system you need to go to red. So that was good. Well, it was also bad, because if you unlock a turnout in front of an approaching train, that can be really dangerous, because the train may not have time to stop. Therefore, how did they fix that? Well, the railroads put in something called running time. And what that means is that the crew unlocks the switch and the signals drop to red, but you can't move the points until time has expired. Usually that's like 5 minutes, 10 minutes. It's specific to the location on the railroad. So that was good. Well, but it was also bad, because if you don't have a train coming, there's no sense in running time. Otherwise the crew's just sitting there, twiddling their thumbs for 10 minutes or whatever. So then the railroads developed what's called a quick release zone. And, and now the only reason I point all this stuff out is it gets back to how prototypical do you want to be. A lot of railroads typically often get down to this point where and don't think about, well, if I unlock a turnout from a train, it can be dangerous. And you see a few railroads will run time. Usually the operators don't like to run time. And I know very few railroads that do the quick release zone. So again, we're down to it's how prototypical do you want to be, and what are the trade-offs? What's going to cost you? So let's talk about how do I bend the iron, or what can I use for moving my points? Well, you got lots of choices. You got twin coils, slow motion motors, stall motors, servo, stepper motors, all kinds of good stuff. You have to ask, where do I going to pull my power from? I'm going to pull from the track. Am I going to need more wires? Um, separate power supplies. If you pull it from the track, then it reduces the power available to engines. Um, Also, if you pull it from the track and you get a short, often you can't move the points anymore. If you pull it from the track, will you trip detectors? But really, the thing I want to point out here is that when you make the decision about what's technology I'm going to use for throwing the points, make sure that your stationary decoder matches it. So read the fine print. Some stationary decoders won't support twin coils because typically a twin coil, you need a big kick in electricity to flip the coils. And some stationary decoders can't do that. So, read the fine print, match up the technology for your switch machine with the type of stationary decoder you're going to use. Let's move to feedback. How do I get feedback? How does the computer know which way the points are aligned? Okay, one way is to put micro switches under the throw bar. Okay, and then the micro switches hook up to the sensor, and the sensor tells the computer. Another way is some of your switch motors have sensors in them. I'm thinking of tortoises with their double throw, pull switches, and so the switch motor can tell you which way the points are lined up. Sometimes the stationary decoders will tell you. So for example, if you send a command to move the points, then the stationary decoder will echo it. The thing to take away from this diagram is that dependability goes from the bottom to the top. If you use, for example, micro switches, those are pretty good in the sense that they'll tell you which way the points are lined up, but they won't tell you if you've broken the points. And I've seen this happen, So in other words, the switch really isn't lined because one of your rails is broken. Okay, the next step then is if you go to the switch motor, not only can you not tell if a rail is broken, but you can't tell if the throw bar actually threw. For example, you may have broken the linkage between the switch motor and the throw bar. If you go up to the stationary decoder, you don't know that the switch motor actually got the change in voltage to flip the motor. Now, I point this out, and that the dependability goes up, and typically the cost goes up as well. It usually costs more to put 2 micro switches on here and a sensor than to take your sensor off of the switch motor and so forth. In reality, this is usually good enough. It's very seldom that you're going to see the points break loose, or you're going to see the linkage between the switch motor and the drawbar break loose. It's all how much do you want to pay for how much dependability. Let's just do the simplest form of doing feedback, point feedback is through detection. And the idea is you just connect, let's say, a 10 or 20K ohm resistor from here to here, and this assumes you're using electrical detection for your block detectors. So consequently, when the turnout is thrown for the normal route, there's no electricity conducting in through here, and your detector will be just fine, and it'll show occupancy when a train goes through. If you throw it the divergent route, you now have opposite polarity between the frog and the stock rail, and you have electricity flowing through the resistor, so consequently show detected. This is the way that railroads originally showed detection, or feedback to knock the signals down. But I think it was the FRA or whatever the administration was at that time said, it's not safe enough because they call them shunts because the shunts may fail. So that's why they went from manual to automatic signaling control. Mechanical feedback is one way. You can put sensors on your throw bar. If you read the big book at Digitrax, it'll say you can have exact feedback, and in which case you put a sensor on each end of the throw bar. That gives you four conditions. You got two sensors, four conditions. This sensor could be detecting, reporting feedback. This sensor could be reporting feedback. Neither one may be, which is nice because that tells you that the points are in motion. If both report feedback, then you know something's broken. Cheaper way and what most model railroaders do is what's called positive feedback, in which you put a sensor on just one side of the throw bar. So consequently, if the sensor is showing fired, it says the points, in this case, let's say the points are in the normal position, and if it's showing that the sensor is inactive, it says that it's in the diverging position, but that doesn't tell you anything about when the points are in transition. Here's another way. If you remember, I showed you where could you get feedback. Let's look at assuming that, well, first of all, let's talk about where the commands come from on a model railroad. Typically, they can come from the computer. So the computer sends a command to the stationary decoder to throw the points. They come from a throttle or a cab. And if your stationary decoder supports it, often they'll give you a flash or push button you can use to throw the points. So, given all that, here's another way you can get feedback as to which way the points are positioned. And I call that feedback being command listener. The computer listens to the bus. So if you're using something like CMRI or LCC, you don't have a cab on the bus, so you won't be able to use it for that. But okay, so the computer throws the points, and you go on the assumption it assumes that everything worked right. The computer said, okay, I told the stationary decoder to move the points. I'm going to assume it all happened. And again, 99.9% of the time, that's a good assumption. Suppose that the operator, the engineer, uses a switch on the cab for throwing the points. Well, the computer will see the command that goes out on the bus to the stationary decoder, and just like as though the computer thought that he moved the points, he can say, okay, I understand that the engineer has thrown the points, so the points are now moved. Often then, and again, like I say, the cab scenario doesn't work if you're using something in which you don't have your throttles on your bus. If you use a fascia push button, often the stationary decoder will then put the same command on the bus, and the computer can see that the points moved. So we've covered all three sources of point movement just by watching for the commands that go to the stationary decoder. Now, okay, who controls the turnout? Well, could be the field crew, and this would be in the case like a manual turnout or the automatic in Chubb's taxonomy. If it's an unpowered turnout, like the automatic, then the field crew can do it. And we have the case of the dispatcher may be able to affect it, but this is if the dispatcher can lock it and unlock it but can't move it. If it's a powered turnout, then it's going to depend upon who controls the turnout. Normally it's going to be the dispatcher, but you need a procedure for transferring control from the dispatcher to the field crew and back. So for your consideration, things that, as you figure out how you want to do this, questions you want to ask yourself. Does the dispatcher have absolute control? In other words, he has to unlock the turnout in order for the field crew to move it. I know of one or two operators who say that's gospel. The field crew cannot move the turnout unless the dispatcher's unlocked it. I know of other people who say I don't want that because I want to be able to unlock them from the field because I don't want to turn the computer on for doing something like maintenance. How does the crew know that they have permission to unlock the turnout? You know, the dispatcher can tell them, you can light an LED to say that's unlocked, something like that. Can the field override the dispatcher? In the prototype, this is true because because for safety reasons, if you lose the connectivity, the code line between the turnout and the dispatcher, then you know the turnouts are basically stuck in the position they are. So for safety reasons, you want the field to be able to override the dispatcher. What steps does the dispatcher do to transfer control or regain control? What steps does the field crew do to receive control or relinquish control? And then the big question, of course, is how do I convert all the above to reality? This is a picture. I think this is a dual control, but the more I look at it, I'm not sure. And the way it works is that the field crew comes out, he unlocks the padlock, okay, removes it. That then lets him take big lever, moves the lever from the hand position, or I'm sorry, from the machine electric position into the hand position, and now he can move the points. Okay, do you want to simulate something like that? If I were to draw that up for functionally how that works on a model railroad, I might do something like this. I've got a double pull, double throw switch here. When it's in one position, the locked position, the dispatcher has control of the switch machine, and there is no local control because electrically it's disconnected. Now the Tam Valley Depot Quad LN, which works with servos, has this automatically. You send a command to the Quad LN, and it basically throws this double pull, double throw. And when it's in the unlocked position, then the double pull, double throws move to here, and now the dispatcher has no control of the switch machine, but we have local control. There's another way you can do this, which is totally in software. And how it works is this: the cab, you've advertised that the crew know that they have to throw this turnout on their cab in order a particular number in order to throw a particular turnout. So they say, I want to request that switch 10 be thrown. That goes into the computer. The computer then looks at the situation and says, yeah, I don't have a route line through there, or there's no, I don't see any danger in throwing that turnout. The computer then issues the command to throw the decoder. In the local net world, there are the high numbered switch commands cannot be accessed through the cab. So then you set up your stationary decoders to listen to be commanded by high numbered addresses, and you tell your operators to use the low number addresses to ask for the points to move, and then the computer then does the checking. That's one way to enforce it. And with this, then the dispatcher has complete control, and you have no field control whatsoever. You can also do it control by override. And the way it works is this. The computer sees that there's feedback. It sees that the points have moved using one of the techniques we've talked about earlier. In other words, the cab had moved the points, or the local crew had pushed the fascia button, the points moved. The computer sees that the points move. The computer says, well, that doesn't work. That's unsafe. And it sends a command to move the points back. It's kind of clumsy because if things happen slowly, the crew will see the points move, and then they'll see them move back. Quickly, they will learn that they can't move the points from the fascia unless the dispatcher has unlocked them. You know, they'll learn. In practical, when I've tried this on some local net Digitrax systems, it happens so fast the crew never sees the points move. Here's another way of doing things, which is a combination of electrical and mechanical. And I'll use it for example. We did this on Pat Lana's in-scale crank layout. He uses tortoise switch machines through a bell crank mechanism to throw the points. Each control point has this little panel. It has a switch key, it has an LED, it has a rocker switch. The definition of the LEDs is if it's green, then it's ready for manual use. In other words, the crew can, the rocker switch is active. If on the other hand, it's red, that says that the dispatcher has locked it. The way it works is this way. Pat was able to find these keys and get all of his sockets keyed the same. And the switch is called a 3-pole single throw switch, and the way it works is this. When the key is in the locked position, all the electrical contacts go back to the SCHC, so the SCHC has complete control of the turnout. And coming off the SCHC, we just do the red LED, green LED from the dispatcher's computer to tell the operator when he has control. When the operator flips the key to the other position, then all the switches throw. And now if you follow the electrical, the SCHC has no control of the turnout, and the rocker switch controls the turnout. So here, the key switch determines completely who controls the switch machine at any time. Here's another example. This is off of John Parker's BNSF Fall River Division. He again uses Digitrax SEHCs. He has a panel for each of his control points. The panel has a key switch in it and some push buttons. The push buttons go to the SEHC. So it's all manual, it's all local type stuff. But he threw in the key switch right in here, such that if you don't have a key in the switch and the switch disengaged, the push button doesn't do anything. And this has a couple of nice features to it. One is that it provides some play value. You know, putting the key into the lock and twisting it is effectively like unlocking the padlock. In addition, when you got an open house and you got people walking around with fingers and they want to say, well, I wonder what this push button does, it doesn't do anything because the lock is in the lock position. You can go even cheaper, get the same effect. One of the problems with a key lock is you got to get all your locks keyed the same, because you don't want to say, well, it's a little bit disadvantageous to say this key is for that, you know, control point, and this is another one's for a different control point. Here, you go with the phono plug. These are readily available. They're cheap. This is your key. So when the phono plug is inserted, you have electrical circuit. When the phono plug is not inserted, then there's no way for the push button to throw the turnouts. So here are the points, talking points on wiring signals. You can use conventional technology. You got multiple feedback choices. Certainty of which way the points are set is proportional to the cost. The balance of remote control against local control makes a big difference in the fun of the operations, and plan before you build. Let's talk really briefly about signals. You got lots of choices. You got semaphores, you got multicolored lights, you got searchlights. I think the important thing is make sure you match your driver electronics to the technology, and we'll look at some samples. Semaphores. Love this. These are some of the few semaphores left in the United States. These are on the Raton Pass Division down in New Mexico of the BNSF. This is east siding switch wagon mount. These are in-scale turnouts. Again, I'm talking about Pat Lana's layout. Notice that we've got vertical, we've got diagonal, and we've got horizontal. So it's a 3-position semaphore. He uses, again, bell cranks driven by tortoise switch machines. what we found on his layout is that it's mostly, semaphores are mostly a mechanical problem. He hand built his semaphores simply because, again, they were cheaper. The problems were, how do you translate the large motion of the tortoises into the small motion required to move the blade? How do you make the fine adjustments? How do you hold the fine adjustments? They're very fragile. We've had problems with reliable pivot points and threading the wire through those tiny tubes in the masts. You have a selection of machines you can use. Again, you got slow motion, you can use stepper motors, you can use servos. We found that the Digitrack SEHC and the Quad LN support the slow motion, and they give you the three positions of feedback that you need to give the three positions of the blades. Signals. This is the east end of Bailey Yard in North Platte. Great place to go and watch trains and signals and stuff like that. Again, you got lots of choices. Incandescent bulbs, which I would not recommend. They get hot. They use a lot. They use more electricity. Go with LEDs. You can use discrete color LEDs. You can use bicolor LEDs. You can use tricolor. Tricolor tend to be more expensive than bicolor. Note, if your LEDs are common anode or common cathode, make sure that your stationary decoders support the LEDs properly. And also make sure that if you have blocks of them, for example, an SEHC, you have to set half the signals the same. And they could be either common cathode or common anode, but each group has to be the same common anode or the same common cathode. Okay, so that's about all on signals I'm going to go into today. How do you want to control? What do you want the signals to do? ABS, APB, CTC. Again, in a future presentation, we'll get much more detail into what these are. So, talking points on signals, there's very little mystery in how to wire them. They tend to be expensive. Protect them from being knocked over. You add a wow factor. They're bright and animated. You can mix and match on the layout, but you have to take care in how you mix and match the drive electronics. And you need to decide what aspects and indications you're going to use, what the signals are telling the crew ahead of time. Let's look at a reference design. People ask, what's it going to cost? And I haven't updated this in several years, but I think these prices are still pretty good. And I'm not recommending particularly these things. I think if you went with Arduinos or some assessed stuff, you probably get different prices. But I think that they're in the comparable range. So this is really just a reference design. You can go higher or lower by some. Basically, I picked out an SEHC because it's one of the most cost-effective ways I know of driving LED signals. I went with the Quad LN because it drives a servo. The servos are cheaper than tortoises by a long shot. The Quad LN also had the internal lock on it so that the dispatcher could lock out local control. The Quad LN also has the push button input for when the local control is unlocked. The Quad LN had a single input, which I then took a BD4 and ran into it. BD4 does not have circuit breaker protection. And when you add all this stuff up, it comes out to something like this. And I know first reaction is you swallow real hard and say $136 per control point. Thing to remember, go back to this, it's money, time, skill, and friends. If we take this cost breakdown, what you find is that the majority of the cost is in the signals themselves. If somebody gave you all this, the electronics and the motors and stuff, that only knocked $36 off of this, you're still at $100. So here is where the real cost is. You want to save money on a signaling system like this. Place to do is, if you got the time, build your own signals or from scratch or from kits. That's the bottom line on this guy. So wrapping up, we focused. I've been very, very myopic in this talk and looking at the hardware and how things are wired together. You need something that ties the pieces together so that they talk to each other, they make the decisions about what the signal should be, when switches are unlocked, when they move, that kind of stuff. And finally, the big one, of course, is where and how does the human fit in. I'll drop off some references for your that you can look at. And with that, I guess I'm ready to take questions.
Hey, thank you, Rodney. And before we open up for questions, I just want to reiterate that this is a conceptual talk to get you to think about what you want out of your railroad. So it's not to scare people to death of, oh my God, it's going to cost a fortune, I can't afford to do it. Those of us that already have large railroads or are planning one, may very well already have an expectation of the cost, where they may do it incrementally. For those who are just starting out, some of the concepts that Rodney discussed are very important before you start laying the track to get the gaps in the right place and stuff like that. And Ryan and Max, you guys said you're just building a layout in a garage, so it's probably a mid-size layout. But one way to implement this slowly is plan ahead where your block gaps need to be. Put the insulators in, and then you drop your feeder wires for each one of those blocks. If you don't want to do the detection and all this fancy stuff right away, you can take all those detection block feeders and just tie them all together and run without detection, but you've already got the infrastructure there to add detection later. Then you can add the detection in. If you have short problems, you can divide those detection blocks into power districts. So you can do this all incrementally. My layout, I've got detection everywhere. The blocks are in. I do not do turnout feedback. And I don't have a single signal on the layout yet. So one of the things that we'll look at in a future session on the tutorials is using CATs for a magnet board type of dispatching, where you may or may not have detection in place, but it can be a mother may I type of scenario where somebody still calls into the dispatcher looks at his board, he may or may not see where the occupancy is based on detection. If you don't have detection, he doesn't see anything, but then he just gives permission for that train to move without the use of signals. So yeah, you can definitely get into it incrementally, but use the information in this excellent clinic, to help you with the design and think ahead so that it's easy to convert later. So with that, I'll open it up to questions. Anything?
Okay. Well, hey, Jerry. Well, thanks. And thanks, Rodney. That was really great. I really appreciate that. That was very, very helpful. So where we are, Jerry, on our layout is basically all the tracks done. Everything's been gapped. We're in our second BDL 168. So we have 32 detection sections that are wired, and then 2 SE8Cs. So basically where we are right now is everything's ready to go. I think we're just looking to be ready for when the CATS classes begin, so to speak, so we can get up and running. So basically I have everything laid out exactly. I think the way that it will look prototypical. Like I said, it's not a huge layout, but it is pretty heavily signaled. So we have short blocks. The blocks are somewhat shorter than you would see normally. But yeah, so that's kind of where we're at, Jerry, on our layout. So we're really looking forward to the tutorials and things like that are coming up. So yeah, I think we're all set up for that. So anyway, I don't want to take any more of your time, but
oh no, that's fine. That's what we're here for. So the pressure's on now. I got to get those tutorials posted.
Right.
Yes,
but I have a young man here. I get a young man here that's eager to learn too, and he's very, very good with computers and stuff like that. So, yeah. So thanks again for all your guys' help. Been very, very helpful. So we appreciate that.
Thank you. Yeah.
So I have a question.
I
have a question, Jerry.
Yeah, go ahead.
So everybody seems like they're using Digitrax for their systems, and I'm using NCE. I wanted to know if anybody here is using NCE, and have they used the Lightits for their signal head aspects at this point?
Hey, Dave, I helped a gentleman on the other side of the state of Wisconsin with his CTC dispatcher panel. It's a JMRI panel. We use Lightits and those, what are those other things that they have there for the block detection? I forgot.
The BD20s.
Yes. We
Okay.
incorporated all that. We used JMRI to interface, and we got it all working. There's a learning curve with the Lightits because they were written by probably the engineer who designed them. And
Right.
Certainly was.
Yeah, and I understand what you're saying about there's a learning curve to that. I haven't actually programmed any of them, but I've read enough pieces about the fact that it's not real easy, but once you know the process, it is easy.
Yeah, I remember when I got my first BDL board from Digitrax, and it was a little daunting at first. But now I've got, I don't know, 15 of them or something like that around the layout. So like Ryan, if you've already got those working, you've got a big chunk of the work done.
Yeah, because
I was Digitrax totally until I had some control issues due to my local environment. And I switched my train control to NCE, but I still use the BDL 168s and the SE8Cs for my signal and turnout control, and use CATs to generate the CTC environment.
My experience has been, Digitrax and NCE by far are the most used systems. Tends to be geographic though. Like around me, everybody uses Digitrax. One guy has NCE, so he had to, back in the day, have 10, 12 cabs for everybody to use because people just didn't bring their own. Of course, nowadays when you got Wi-Fi and you can run a train with your phone, that argument's kind of gone away. But like in North Jersey, everybody's on NCE. But then, as you mentioned, people on NCE sometimes use the Digitrax detection or the SE8s to drive their signals. That just gets it on a separate bus, which of course people were doing that with NCE 10 years ago. Now everybody's starting to look at LCC to have a separate bus. I've got all mine on the same Digitrax LocoNet bus. At some point, maybe that'll be a problem. Digitrax did come out with a repeater about 2-3 years ago. I got one of those, and that solves a lot of issues I was having. But yeah, you can intermix the technologies, whatever works best.
But I disagree with you, Jerry. The fact that around us, because since we don't live far apart, in this area, a lot of places that I visited during the open houses at the end of the year, there is a lot of NCE floating around.
Where are you?
Over at Mount Joy.
Oh, Mount Joy. Wait, you got to cross the river to get there.
Well, yeah. You got to get the ferry.
Yeah, no, I know there are more over there in.
And I've been to your layout up in Edders.
Oh, have you?
Yes.
Yeah, haven't been open for a while, unfortunately. But yeah.
Yeah, it was, and it may have actually been your layout before this one, maybe.
The N scale one.
Yeah.
Yeah, I've been HO now for about 10 years.
Oh, okay.
That goes way back. And I had a big CT CATS board then.
Right.
Yeah, Lancaster County, I do know quite a few NCE users over there. Now, Cumberland, York County, everybody over here is Digitrax.
Right. So what I'm taking is that the NCE switch 8 for the thing is the same as a stationary decoder. Is that correct?
Yes. So a stationary decoder.
I think a lot of it's terminology associating the item with what is being said. I mean, up until here for about a little while ago, I didn't know that's actually what the stationary decoder was. I mean, I got thousands of dollars tied up in my NCE stuff, on my layout that I'm building, but I still don't know some of the general terms. I'm kind of interested to see Rodney's piece to explain the difference between CTC and ABS and stuff to decide which way I really want to go. But all the block detection and all the sensors and all the AUIs or AIUs that supply the signals back to the computer are installed at this point. So, and I have a lot of the BLMA stuff that I collected over the years, so I'm good there. But yes, Dave.
The gentleman uses all the stuff you're talking about. The Lightits, I really like the Lightits, and they're very, very flexible. All the other stuff he uses over there works phenomenal, but he uses combination. He's got Semaphores and target signals. So everything that you were talking about, our desire to put on the layout with the NCE switchits and Lightits and AUQs, whatever those things are, it does work, and he made it work. But we did have a problem with the terminology.
Yeah,
Right.
so the stationary decoder, it's a decoder, much like you put in a locomotive, a lot less features, and they often they stay in one place. They're attached to your benchwork somewhere, or maybe velcroed right onto the switch machine, as I often do with my tortoises. But back to your point earlier, David, we're talking, Digitrax, NCE, whatever. My command station's Digitrax. I use Digitrax BDL 168 for detection, but all of my stationary decoders are NCE switches.
Right.
Yeah, and actually, that's one of the things that needs to be, footnoted. Not all stationary decoders support the same features. Some of the flowcharts that Rodney was showing, for instance, like the Switch 8, doesn't have that way to tell if you use the fascia input that it provided, it didn't have a direct feedback to the rest of the systems.
Right.
So, like, the computer can't monitor that.
It didn't feed back to the computer, correct?
Right.
Okay.
That was one. That was one gotcha. Even the SE8C in certain configurations doesn't give you the right. If you're doing certain things with the different input bits, you don't necessarily get the local control fed back to the computer in an easy way.
Right.
But this is one little gotcha that. Yes, not all stationary decoders are designed the same, and some of the features will vary. And the last was on the Lightit, the biggest headache was, and I can't remember which NCE system it is, but one of them, it needs a firmware update because it can't generate the right packet for the Lightit to interpret. If you're going through JMRI, it's fine. JMRI makes the 5-byte or 6-byte packet. It's for the aspect signaling, I think. And the light is happy, but you can't do that from the handheld throttle.
That's correct. The cab 06 is the problem.
Right.
But apparently they're going to fix that. So, but like you're saying that the push buttons on the fascia don't kick back a signal back to the computer, but I'm not using them, so I'm out of that little boat.
Yeah, me too.
Yeah.
And I think, what Rodney addressed in this talk was these are things to think about. When you're going to pick a stationary decoder, you've got to match the technology with what you want to do. And getting into what the different boards, the different brands can do is kind of beyond the scope of this talk. But it suggests maybe we ought to have a bull session sometime and talk about stationary decoders and which ones do what, and talk about this, that, and the other thing that Dave's saying. Yeah, all right, yeah. So those are the kind of things that maybe we can add in as this conversation continues to evolve.
Well, one of the great things about CATS is that it rides on top of JMRI, which gives you, abstraction layers for just about every kind of hardware that exists. So, in the words of, what was it, Hitchhiker's Guide, it's the universal babblizer. You can get all these things.
It's the Babelfish.
Yeah, the Babelfish, right, yeah.
And I was thinking of Star Trek with the universal translator. Yeah.
Yeah. Yeah, well, sadly, most of us are at the point where we're sticking stuff in our ear all the time, and they're not helping much.
Doesn't make it clearer.
Just makes it louder.
It's always huh.
Yeah.
Yeah,
Huh?
yeah, me too, Dave. Yeah. But anyway, yeah, JMRI is your friend there. So, if you want, like Rodney says, be sure that you've got the hardware that matches the stuff on the layout. But once you find it, it's usually relatively cheap to interface a bus for that stuff to JMRI. And once you've got it in JMRI, you can do anything you want with it. And it'll talk to its neighbor, even if it's, in the other church. And, CATS, of course, is yet another layer up, so you just don't have to deal with it very much.
Right.
Another thing that I had some problems with JMRI is that I didn't understand how the JMRI and the turnouts table automatically generated NT numbers, from NT, whatever you want to do. I didn't know what the heck NT was, and I finally found a piece in the help section of JMRI, which was not easy to find, that explains all the codes and which different manufacturers and everything.
Yeah.
I mean, there's so much information in the index of the help of JMRI, it swamps you to a point that you just don't know what to do with it.
Yeah,
I use the analogy of drinking from the fire hoses with a lot of the information. Particularly when you ask certain questions on the group list, unfortunately, the poor person frequently gets overwhelmed with the amount of data that gets thrown at them.
Right. And some of the information I would love to see, like if it was segmentized, related to what system, that's some of the major systems that you use, so you'd have an understanding to it. But that's way major past anything that could happen.
Yeah.
Well, people have started
definitely
hashtagging
trying
on
to
the
keep
stuff
it up
so
to
you
date.
can search on it. I'm sorry, Jerry. Go ahead.
Sorry, Seth.
What I was saying is a lot of people have started to, put hashtags or pound plus a label on these things, so you can you can go search the archive with a tag and at least get a somewhat more focused collection of stuff.
Right.
And if you didn't know, when you're using Groups.io and you post an email, you can put tags in the bottom of your email and it will index it.
Okay.
Anything else? All right. Thanks a bunch. Thanks for joining us tonight. And we'll get the next session scheduled shortly. And I promise to have some tutorials posted about Thanksgiving weekend. All right. Take care.
Thank you, guys.
Thanks, Jerry.
Bye-bye.
Bye. Thanks.